Welcome to Caltrans LSIT LS exam preparation course. One aid in your preparation for California licensure examinations. A word of caution, don't use this course as your only preparation. Devise and follow a regular schedule of study which begins months before the test. Work many problems in each area, not just those in this course's workbook, but problems from other sources as well. This course is funded by Caltrans, but you and I owe a profound thanks to others, the course's instructors, from the academic community, the private sector, other public agencies, and from Caltrans as well. We wish you well in your study toward becoming a member of California's professional land surveying community.
Hi. Welcome to the Photogrammetry unit of the Caltrans video training course. My name is Dick Burns. I'm chief of the headquarters Photogrammetry section for Caltrans. In this training unit, we will be demonstrating or reviewing basic photogrammetric concepts as applied to surveying practice. Definition: photogrammetry is the art, science, and technology of obtaining reliable information about physical objects and the environment through processes of recording, measuring, and interpreting photographic images and patterns of electromagnetic, radiant energy, and other phenomena. This definition is from the 4th edition Manual of Photogrammetry, published by the American Society of Photogrammetry and Remote Sensing. Applications. In the field of land surveying, we are primarily concerned with the photogrammetric applications involving aerial photography and mapping, including the ground location of physical objects, lines, and points, and the determination of earthwork quantities. Course objectives. The objectives of this course are to acquaint the student with the basic principles of photogrammetry in order to gain the understanding to plan the execution of photogrammetric projects as required on the land surveyor's examination. This video will provide the first step in your understanding of the photogrammetric process. However, to be able to confidently solve the photogrammetry problems on the land surveyor's test, you will need considerably more study and practice. Now let's begin to examine the basic principles of photogrammetry. Number 1, cameras. The aerial camera is a vital part of the photogrammetric mapping process. The metric quality aerial cameras used for photogrammetric mapping are very precise instruments with virtually no distortion from the object space, ground, to the image space, photograph. Here we see the camera being loaded and mounted in the aircraft by the pilot and aerial photographer. The mapping cameras come in several focal lengths. 4 common focal lengths are 3.5 inch, considered in photogrammetry to be a super wide angle, 6 inch wide angle, 8.25 inch normal angle, and the 12 inch narrow angle, with the 6 inch camera by far the most widely used. Most of the aerial cameras currently in use are manufactured in Switzerland and Germany, and new cameras are priced in the $300,000 range. Focal length. The focal length of a camera affects the scale of the photography for a given flying height and the angle of coverage of the photograph. The 3.5 inch and 6 inch cameras would be considered as wide-angle lenses in a commonly used 35 millimeter camera, while the 8.25 inch would be the normal lens, and the 12 inch would be more like a telephoto. As with handheld 35 millimeter cameras, the longer the focal length, the greater the magnification, and the smaller the field of view. Conversely, the shorter focal length yields less magnification and a wider viewing angle. In this graphic, we see the comparison of the photoscales of 6 and 12-inch cameras flown from the same flying height. The 12-inch camera yields a scale twice as large as a 6-inch camera and covers 1/4 of the area. Here we see the comparison between the 8 1/4 and 3 1/2-inch cameras. Note that the 3 1/2-inch camera covers a large area at a small scale, similar to a 35 millimeter wide-angle lens. Flying height focal length relationship. Here we see 4 cameras flying at different altitudes but photographing at the same scale. Compared to a 6-inch focal length camera, a longer focal length lens will allow a higher flying height, and a shorter focal length lens will allow a lower flying height, all yielding the same photoscale. In this presentation, we will direct your attention to the 6-inch focal length camera due to its extensive use, but you should be aware of the capabilities of other mapping cameras. Format. The cameras we will be concerned with in this presentation will have a 9-inch by 9-inch format. All aerial mapping cameras have fiducial marks, usually 8, around the perimeter of the camera frame, which appear in the photographs as small white measurement points. The main purposes of the fiducial marks are to define the optical center of the camera lens and to check for film distortion and film flatness in the focal plane. The cameras are calibrated by the U.S. Geological Survey for lens distortion, fiducial mark coordinates, model flatness, and other parameters. Number 2, scale. Map and photo scales are expressed in various forms, such as 1 inch equals 250 feet, 1 to 3,000, 1 inch over 250 feet, 100 scale, or 1 inch equals 4 miles. These various forms of scale represent units on the map or photograph in relation to units on the ground. The large scale, small scale relationship can be confusing. For example, 1 inch equals 50 feet is a larger scale than 1 inch equals 100 feet. Some methods to visualize and remember this relationship are that a building, as shown here, would appear larger on a 50 scale map than the same building would on a 100 scale map, or that the ratio 1 to 600 representing a 50 scale map is larger than 1 to 1200 for a 100 scale map. To plan a photogrammetric project and check the photography for usability on the project, the scale relationship must be understood. Basic formulas. S equals F over H minus small h, where S equals scale, F equals focal length of the camera, H equals flying height above sea level, and small h is the elevation of the mean terrain. This is the basic scale formula, and it is derived as shown on this diagram. Small d is a distance on the photograph, and d is a corresponding distance on the ground. By corresponding sides of similar triangles being proportional, small d over d equals F over H minus small h. Or since small d over d equals scale, then S equals F over H minus small h. Scale is also expressed as a denominator with 1 as a numerator, such as 1 over 3,000. A ratio. 1 of any unit on the map or photograph equals 3,000 of the same units on the ground. Or with units such as 1 inch over 250 feet. Frequently, we know the scale and need to solve for the flying height above sea level, h. Therefore, we can convert the basic scale formula, as in the middle equation in the graphic, to 1 over x equals f over h minus small h, with x representing the scale denominator, with 1 as the numerator, and solve for h. Cross-multiplying, we have h minus small h equals x times f. Solving for h, we have h equals x times f plus small h. Now let's take time to look at the diagram again and see that scale can be in these three forms. S equals f over h minus small h equals small d over d, and equals, when the numerator is reduced to unity, 1 over x. When the scale is reduced to unity, 1 over x is actually the reciprocal of small d over d. Although it is not shown on the graphic, f is often stated in millimeters, so the number of millimeters per inch, 25.4, is a number which should be among those committed to memory. Again, remember that S can be in these three forms: f over h minus small h, small d over d, and 1 over x. Now we'll take a few seconds to absorb these relationships. Number 3, flying height. When planning a photogrammetric project, the flying height may be computed by returning to the basic scale formula or solving directly for h, as shown above. For example, to photograph at a scale of 1 inch equals 250 feet with a 6-inch focal length camera over terrain with a mean elevation of 1,200 feet, what is the required flying height above sea level, h? We can start at the beginning basic formula and go through all the steps using these numbers, or go to the bottom formula and solve directly for h. Let's do that. H equals x times f plus small h, or h equals 250 times 6, which is 1,500, plus 1,200, the mean terrain elevation, so h equals 2,700 feet. Now we can also solve the equation by converting all the numbers to feet. If 1 inch equals 250 feet, then 1 foot on the photo will equal 12 times 250, or 3,000 feet on the ground. Here the scale is a ratio of 1 to 3,000. The 6-inch focal length will convert to 0.5 feet. The equation will be h equals x times f plus small h, which is h equals 3,000 times 0.5 plus 1,200, or h equals 1,500 plus 1,200, and again h equals 2,700 feet. To verify that the photography was flown at the correct altitude for the project, again solve for h. If the photography has premarks with known coordinates, divide the ground distance in feet, d, by the photo distance in inches, small d. This is the reciprocal of small d over d, reducing the photo scale to unity and determining x. Then multiply the result by the focal length in inches and add the mean premark elevation. The result of these calculations is the flying height above sea level. If the control values for the photograph are not available at the time of checking, the ground distance between features on the photo can be determined from a quad map. Terrain height. Terrain height, small h, is the mean elevation of the mapping area along the flight line. Terrain height is normally determined from a USGS quad map or other contour maps. C-factor. C-factor is the flying height above the mean terrain divided by the contour interval, h minus small h over the contour interval. C-factor is the formula to determine the accuracy of the entire photogrammetric system, including the flying height, the camera, the film and film processing, the diapositive and diapositive processing, the photogrammetric mapping instrument, and the instrument operator. 1500 is a conservative maximum C-factor. This means with a flying height above mean terrain of 1500, a 1-foot contour map may be produced, or at 3,000 feet, a 2-foot contour map. Some photogrammetry firms have stated much higher C-factors, up to and above 2,500. These claims are made for economic reasons, such as fly higher, less ground control, and fewer models, etc. These are all strong incentives to state a higher C-factor than can be realistically achieved, and the use of C-factors higher than 1,500 must be considered on that basis. Flying tolerances. An aircraft on an aerial photography mission cannot fly exactly at the planned flight line at the planned altitude and must be given a reasonable amount of allowable error. Caltrans uses 1/2 inch at photo scale on either side of the flight line for horizontal tolerance, and 5% of the flying height at scales up to and including 1 inch equal 400 feet, and 3% of the flying height at scales smaller than 1 inch equals 400 feet for vertical tolerance. Overlap. Mapping photography is normally planned at 60% overlap. 60% overlap means that each successive photograph overlaps the photo before it by 60%. If there is 60% overlap, there is 40% gain, new area photographed, with each successive exposure along the flight line. An aerial photograph is 9 inches. 40% of 9 inches is 3.6 inches. Therefore, 9 inch by 9 inch photography with 60% overlap has a gain of 3.6 inches on the photo regardless of scale. Here we see the overlap from a side view. Caltrans overlap tolerance is from 55 to 65%. Number 5, side lap. Side lap is the area of side overlap between two adjacent flight lines and is calculated the same way as overlap. Side lap is normally planned within a range of 25 to 40%. Here we see the side lap concept from an in view. Number 6, model concept. A model is defined as the area along the line of flight between centers of two overlapping aerial photographs and bounded parallel to the flight line on each side by a line 1 inch from the edges of the photograph. This is often referred to as a neat model. The normal size for a neat model is 3.6 inches along the line of flight with a 7-inch width. For flight planning, this is reduced to 6 inches to allow for horizontal flying tolerance. The length of a neat model will be changed due to a variation in overlap, and the width may be reduced due to crab, the camera not being square to the flight line, in one or both photos. Stereo vision. Stereo vision is achieved by the left eye viewing the left photograph of a model and the right eye viewing the right photograph. The ability to see the same images from different angles with each eye enables three-dimensional viewing or stereo vision. When viewing the model, the operator sees a measuring or floating mark which appears to be floating above, on, or digging into the ground. The floating mark is used as the point of measurement in all three axes, much the same as surveying instrument crosshairs. Models and flight lines. The concept of a model can be confusing when planning aerial photography because the first model doesn't begin until the center of the first photograph in the flight line. This means that the entire first half of the first photo and the last half of the last photo in a flight line cannot be used for mapping because these images appear in only one photograph and will not allow stereo vision. In this diagram, we can see the relationship of the photography to the flight line. We can only map an area from the center of the first photo to the center of the last photo in a flight line. We can also see that it always takes one more photograph than models to map a given area along the flight line. In this diagram, we see the flight line shown as models rather than photographs. This is the form used for flight planning purposes. Flight path. A flight crew usually consists of a pilot and an aerial photographer. To fly a flight line, the pilot selects landmarks from the map to orient the aircraft and selects the correct altitude using the altimeter. A dry run is often made to make sure the flight line is correct. On the photo run, the photographer is responsible for the operation of the camera and keeps the pilot correctly aligned. The photographs are taken at the proper intervals to ensure correct overlap by a mechanism in the camera. At 1 inch equals 250 feet photo scale, the aircraft is flying at 1,500 feet above the terrain, taking photos at 900-foot intervals. When the end of the flight line is reached, the pilot will turn the aircraft in two 180-degree turns and align with the next flight line. Models in blocks. Blocks consist of parallel or nearly parallel flight lines. The photography from parallel flight lines must have side lap in order to be usable and cannot have any gaps. The amount of side lap usually ranges from 25 to 40%. To calculate the photo distance between flight lines, subtract the side lap percentage from 100% and multiply by 9, the photo size. For example, 25% side lap, 100% minus 25% equals 0.75 times 9 inches equals 6.75 inches between flight lines. Number 7, photo control. A well-controlled, neat model requires the following points. 3 well-distributed horizontal control points to set the model scale. Occasionally, 2 horizontal control points are permissible, but the third provides a check. 1 vertical control point located at each of the 4 corners of the neat model for leveling. These points are commonly referred to as wing points. The photo control for a mapping project is normally marked by placing cloth or painted targets over the ground control points prior to aerial photography. This process is called premarking, and the targets are called premarks. It is possible to identify the control points after the photography is taken. This process is called photo identification or post-identification and is less certain and accurate than premarking. Premarking is the preferred method of photo control. Aerotriangulation. Aerotriangulation is a computerized procedure used to reduce the number of pre-marked, field-surveyed control points necessary to map a project. Every model requires 4 wing points to level and 2 or 3 horizontal points to scale it. Using aerotriangulation, some of the points are artificial or pug points marked on the photos with mathematically derived positions and elevations instead of being field surveyed. Virtually all of Caltrans mapping is done with aerotriangulated control. Mapping control requirements vary somewhat with the organization's mapping system and the use of maps. At Caltrans, we are concerned with the vertical accuracy along the roadway, and our standards are conservative in that respect. That is, more vertical control along the flight line. Caltrans control requirements for 1 inch equals 50 feet mapping using aerotriangulation are a pre-mark with horizontal control in each 4th or 5th model, beginning and ending outside the mapping limits, no extrapolation. A minimum of 3 horizontal points in each flight line are required, including points common to other flights. Pre-marks with vertical control along the wing point lines outside the mapping limits at approximately 1,800-foot intervals on alternate sides of the models. Pre-marks with vertical control in the corners of each flight line. Pre-marks with vertical control set at 450-foot intervals within 250 feet of the flight line. Common horizontal and vertical pre-marks may be used where 2 or more flight lines join to save field costs. Common horizontal and vertical pre-marks may also be utilized between parallel flight lines. Block photo control. Block photo control requirements seem to vary considerably with the organization and the individual control planner. There is one area of agreement, however, and it is that the perimeter of the block should be well controlled with no extrapolation. The graphic shows a typical example of block photo control. Caltrans, because we are mainly concerned with highways, does more single flight line mapping than block mapping. Premarking. Premark requirements. A symmetrical pattern around the photo control point is one of the prime requisites for a photogrammetric premark. For large-scale mapping, it is important to have a separation between the center point of the premark and the legs. This configuration allows a discrete point to be read in the photogrammetric instruments rather than guessing at the intersection of a solid cross. Cloth premarks are normally used on natural ground, and painted premarks with the same dimensions and a dull black background are used on pavement. Cloth premarks may also be used on asphalt pavement where traffic is light. Caltrans premark requirements for various scales are shown in the quick reference table in your workbook. Premark placement. Premarks must be exactly centered over the point they identify to maintain scaling accuracy. Premarks are read to a least ground reading of 1/100th of a foot in an analytical plotter using 1 inch equals 250-foot photography. All premarks should be placed in positions which will ensure their appearance in the models they are to control. A premark which appears in only one photo is useless. Premarks should be placed where they are visible in the photos they control, in the sun at the time of photography, and check to make sure they are in place immediately prior to photography. Accuracy specifications. Caltrans uses the photogrammetric mapping accuracy outline in the Manual of Photogrammetry under Photogrammetry for Highways Committee, 1968. Simply, these accuracy specifications state that 90% of the contours shall be within a half a contour interval and all within one contour interval. 90% of the well-defined planimetric features shall be within 1/40th of an inch and all within 1/20th of an inch. And 90% of the spot elevations shall be within a quarter contour interval and all within a half a contour interval. The accuracy of photogrammetric work is based on field surveys which presumably have no discernible error. There is another similar set of specifications for general large-scale photogrammetric maps in the Manual of Photogrammetry, 4th edition. Both versions of these specifications are widely used. Number 9, mapping. Instruments. There are two general types of photogrammetric plotters used for mapping. The analog plotters, which recreate the photogrammetric model by positioning the photographs in the same scale position with the same tilts existing at the time of exposure, thus creating the model to a smaller scale. The newer type of plotters, called analytic plotters, are computer assisted and create the model by positioning the photographs in a plane and using the computer to simulate the tilts of the photography in space by computer-controlled incremental movements in the X and Y directions. There are many photogrammetric instruments available for mapping purposes. In California, the most widely used analog plotters are Wild A10, B8, Santoni 2C, Galileo G6, G8, Zeiss Planacart, Zeiss Jena Topocart. The most widely used analytical plotters are the Zeiss C120 and P3, the Kern DSR11 and DSR14, and the Wild or Leica BC1, BC2, and BC3. Base sheets. Base sheets are the blank maps which control and the grid ticks are plotted to provide the horizontal and vertical datums to set up the models and begin plotting the maps. These maps provide the points which are located on the photos as premarks or pugs and plotted in the correct coordinate position on the base sheet to allow the plotter operator to orient the model to the ground both horizontally and vertically and draw the map. Base sheets are normally 5-time enlargements of the nominal photography scale. Diapositives. Diapositives are a positive print of the aerial photographs on either glass or mylar. Diapositives are printed on transparent materials in order to use them on photogrammetric plotters. The pugs are drilled in the photographic emulsion of the diapositives. Table enlargements. Photogrammetric mapping is usually a 5-time enlargement of the aerial photography. However, with an automatic table, the enlargement ratio can be set for an enlargement of up to 20 times. A pen or pencil of the table follows the movement of the plotter measuring mark at the set enlargement ratio, thus drawing the map. Computer-aided drafting and design, or CAD mapping. Photogrammetric plotters may work in conjunction with a CAD mapping system to draw the map directly into the computer instead of making a hard copy. Using conventional methods, a manuscript is created on the plotter and then finished drafted and finally digitized into the computer. The direct process avoids the map drafting and map digitizing steps to create the CAD map. Here we see the map as it is displayed on the screen on an editing workstation. Photogrammetric project tasks. Let's go over the steps necessary to complete a photogrammetric project. Number 1, mapping limits. The first step of the photogrammetric mapping process is the determination of the mapping limits. The mapping limits are usually determined by the engineer requesting the mapping. Number 2, required scale and contour interval. The engineer will usually request the scale and contour interval needed for the map. The scale and contour interval is somewhat fixed by the proposed use of the map and the terrain. Number 3, flight plan. The flight plan gives the length and direction of the flight lines and the altitudes above sea level for the pilot and the aerial photographer to photograph the project. These are templates showing the models at 6-inch mapping width. These templates are made for several mapping scales and are made to be used on a 1 inch equals 1,000 feet enlargement of a USGS quad map. The simple template greatly eases the flight planning process. Number 4, control plan. The control plan shows the surveyors where to place the field control, which through arrow triangulation will provide the mapping control. This is the completed flight and control plan. Number 5, place premarks. The premarks are placed over the control using either cloth or paint. They must be precisely placed over the point and maintained so they're visible at the time of photography. Number 6, survey premarks. The horizontal and vertical or vertical only values for the photo control are tied from the project control. Good surveying procedures must be used. All points must be turned through or have an independent check. Surveys do not have to be completed before the aerial photography, but the premarks must be in place. Number 7, aerial photography. Aerial photography should be ordered from the project site to ensure that the weather is clear in the area to be photographed. Good aerial photography requires a great deal of skill to accomplish, but is done in a short period of time in relation to the other tasks. Number 8, survey calculations. Survey notes must be reduced to coordinates and elevations of the photo control. Number 9, check aerial photography. The aerial photography is checked for coverage, overlap, flying height, tilt, image motion, and pictorial quality. Number 10, arrow triangulation. Arrow triangulation densifies the skeleton ground control to provide sufficient photo control to level and scale the models. Number 11, base sheets. Base sheets are the blank maps with only the field and arrow triangulated control plus the grid ticks plotted. The control is used to scale and level the models, and the maps are compiled on the base sheets. Number 12, map compilation. The maps are compiled one model at a time, usually on 3 model sheets or into a CAD file. To compile planimetry, the operator traces the feature with the measuring mark on the surface of the feature. For contours, the operator sets the elevation of the contour in the plotter and traces the contour with the measuring mark just skimming the ground. Number 13, map checking. Maps should be independently checked by either photogrammetric or field methods for conformance to specifications and correct mapping symbology. Map corrections. If the maps do not meet specification, then corrections are required. Number 15, map acceptance. The final maps are accepted when the required corrections are completed. These are the 15 steps photogrammetric mapping normally follows in a production environment. Now let's work the photogrammetry problem on the 1991 land surveyor's test. Problem statement. Your client owns sections 9 and 16 and the westerly 4,000 feet of sections 10 and 15, Township 4 South, Range 23 West, San Bernardino Basin Meridian. You have been asked to provide horizontal and vertical control for the topographic mapping that is to be used for planning purposes. Vertical photography taken with a 6-inch focal length camera on a 9 by 9 inch focal plane is to be used. Analytical bridging, arrow triangulation, is not to be considered. The following factors control the project. Make no assumptions. Number 1, a 5-foot contour interval is required. Number 2, model size is 3.6 inches by 7 inches for a single flight line and 3.6 inches by 6.3 inches for 2 or more adjacent flight lines. Number 3, the C factor to be used for this project is 1800. Number 4, the map is to be compiled at a 5-to-1 ratio. Number 5, the average terrain elevation is 2,500 feet above sea level. Number 6, the minimum target size to be used for pre-marking on the ground is not to be less than 1/1000th of an inch by 100th of an inch at the photo scale. Number 7, per a recent record of survey, each section has been found to be of standard dimensions. Problem requirements. Number 1, based on the above specification, determine the following. Show all work. A, the minimum number of flight lines required, 3 points. B, the required flying height above sea level, 3 points. C, the minimum number of models required, 3 points. D, the minimum number of photographs required, 3 points. E, the minimum number of horizontal and vertical control stations required to provide adequate checks, 5 points. F, the negative scale, 3 points. G, the nominal map scale, 3 points. H, the minimum length and width of the target placed on the ground as a pre-mark, 4 points. Number 2, give the accuracy requirements for each of the following based on the requirements of the National Map Accuracy Standards. A, contours, 1 point. B, spot elevations, 1 point. C, planimetric features, 1 point. Problem solution. Let's start with the determination of the mapping limits, which are 1 mile plus 4,000 feet in the easterly direction and 2 miles in the northerly direction. So the mapping limits are 9,280 feet by 10,560 feet. Now we have to determine the answer to problem 1B, the flying height above sea level, using what we have to work with: the contour interval, 5 feet, and the C factor, 1,800. The C factor equals h minus small h over the contour interval. When we insert the given numbers, we have 1,800 equals h minus 2,500 over 5. Or solving for h minus 2,500 equals 9,000, or h equals 11,500 feet. Then h minus small h equals 9,000 feet. Now we know the answer to 1B, h, is 11,500 feet. Since h minus small h equals 9,000, we can determine the answer to 1F by using the scale formula S equals F over h minus small h, or S equals 6 inches over 9,000 feet, or 1 over x equals 6 over 9,000, or 6x equals 9,000, or x equals 1,500. The answer to 1F, the negative scale, is 1 inch equals 1,500 feet, or as a ratio, 1 to 18,000. We were given that the map is a 5-time enlargement of the negative scale. Therefore, 1 over 1,500 times 5 equals 1 over 300. So the answer to 1G, the nominal map scale, is 1 inch equals 300 feet, or 1 to 3,600. Now let's look at the area we can map with one model, which has a 3.6 inch by 7 inch size. 3.6 times 1,500 equals 5,400 feet, and 7 times 1,500 equals 10,500 feet. So one model will map an area 5,400 feet by 10,500 feet. So two models flown in the north-south direction will cover an area of 10,800 feet in the north-south direction and 10,500 feet in the east-west direction, adequately covering our mapping limits of 10,560 north-south and 9,280 feet east-west. The answer to 1A is one flight line. The answer to 1C is two models, and since there is one more photo than models per flight line, the answer to 1D is 3 photographs. We need to answer 1E, the minimum number of horizontal and vertical control points to provide adequate checks. 3 vertical control points form a plane, so that is the minimum number to level a model, and the 4th provides a check. To scale a model requires a minimum of 2 points, and the 3rd provides a check. Let's look at the little diagram at the top of this graphic. In the first model, at the bottom of the little diagram, there are 3 horizontal control points and 4 vertical control points, but 2 of the horizontal and 2 of the vertical control points will also control the second model. For the second model, we need to add 1 horizontal and 2 vertical points for a total of 4 horizontal and 6 vertical. This is the grading plan answer to 1E. The planners at Caltrans would have had vertical control on the 4 horizontal control points and vertical only on the remaining 2 points. The real-world answer, as shown on the little diagram, would have been 4 points with horizontal and vertical control and 2 vertical-only points. This answer was not in the grading plan, but may have held up under protest. Problem 1H asks for the minimum length and width of the target placed on the ground as a premark with given dimensions on the photos. Since the photo dimension is 10 times as long as it is wide, and premarks are usually crosses, this might be better described as the minimum length and width of a leg of the target rather than the length and width of the target. Anyway, the photo scale is 1 inch equals 1,500 feet, so 1,000th of an inch would be 1.5 feet, and 100th of an inch would be 15 feet. Problems 2A, 2B, and 2C ask for accuracy requirements for contours, spot elevations, and planimetric features, respectively, based on the National Map Accuracy Standards. Here there is a problem with the grading plan answers. The answers are contours 90% within a half a contour interval, or 2.5 feet. Spot elevations 90% within a quarter contour interval, or 1.25 feet. And planimetry 90% within a 1/30th of an inch, or 10 feet. 2A and 2B grading plan answers appear to be from the reference guide outline, the Photogrammetry for Highways Committee, 1968, as stated in the 4th edition of the Manual of Photogrammetry. Answer 2C appears to be from the general national map accuracy standards for publication scales larger than 1 to 20,000. The old third edition of the manual of photogrammetry does have accuracy standards for highways divided into two classes, one for 40, 50, 100, and 200 feet to the inch, and the other for 400, 500, 800, and 1,000 feet to the inch. The grading plan answers match the latter, but the 300 scale photography from the problem doesn't match either set of standards. The grading plan answers don't seem to fit any of the accuracy specifications. In the final analysis, this is a good practical photogrammetry problem with a couple of areas which may require protests. This is not unusual. Most of the photogrammetry problems do have ambiguous parts to the questions. This is sometimes because there are different planning variations which will still meet specifications, and sometimes they're just plain wrong. Your best defense is to study and understand the basic principles, read the questions carefully, and use calculations based on the problem information, even if it's wrong or impractical. For gross errors or omissions, make assumptions in writing and be prepared to protest. Show your work. Be careful. Some problems are tricky even for us old photogrammetrists. Use your workbook, plus work the problems from old exams. Get comfortable with basic photogrammetry. It's not that difficult. There are some relatively easy photogrammetry points waiting for those who have prepared. Good luck.